Hello.
Hello.
Am I audible?
Yes.
Yes, yes.
All right. So like we will start by 45. Okay. We'll just for wait for 4 more minutes. Yeah. So I think we can start the session, right? Just give me some thumbs up if you are able to hear me. So yeah, hello everyone. Uh, First of all, I welcome you all to today's session. So as you know, we have launched a new series of lectures which deals with the concept of rocketry. And this today we are actually gathered here for the first lecture of the five. And so, firstly, I'd like to formally welcome you, every one of you, to this event. And I'll give you a brief. So I'll give you how we're going to do this. Okay. So we're going to start with a introductory session. So right now I'll be giving you guys an overview. So you might have some vague idea about what we are trying to do here, and I'll explain why we are doing this right now. So I believe that all of you have registered for the Rocketry Challenge, right? So today's session and the upcoming sessions, that is the five sessions in total, is more like a prerequisite for our grand final Rocketry Challenge that we are planning towards the end of this month. So what we are intending, what our intentions are, well, basically we are trying to give you guys an insight into the field of rocketry. So you might, so we'll be having different sort of people in your community. Some of you might have already have an idea of what rocketry is, what rockets are. Some of you might have even gone into the mathematical part of the rockets to an extreme deep level. And some of you might be having a peripheral knowledge of, okay, there is something called rocket. So this might be how it works and all those things. So what we're trying to do is actually take you all into consideration and give you guys something out of the session so that you guys can build upon the basic knowledge that you gain from the session. So eventually, we will be having the final rocketry challenge that will be happening on towards the end of this month. The exact date and everything will be announced once the registration closes. That will be on 14th December, as already mentioned in our social media posts. So yeah, we'll give you a more deep insight into the session much later. So by the end of the five lectures, you'll be having a basic idea of how rocket works, what are the different types of rocket, and some of the relevant softwares that you might that might come in handy when you're trying to design rocket of your own. Okay. So attend all the sessions, learn something from it, and more importantly, try to do something on your own. So all these sessions are more like an open-ended question. So you have to fill in your own thoughts in the end, and basically you have to work on whatever you learn from here on your own, and try to come up with concepts or explore the field in general. And we will be having a dedicated team here as a point of contact for all of you people, so that if you guys are having any query, you can contact your point of contact and connect with us so that we might be able to help you. So through this particular event, we are aiming to do two things mainly. The first thing is to spread the awareness of the relevance of rocketry and a basic understanding or insight of how it works and everything. And second thing is to actually engage you in something active. So usually we have a lot of series, talk, and everything going on online. But this time we're thinking of giving you a couple of talks which might actually give you some motivation to do something on your own. So I request every one of you to attend all the five lectures and try to exploit it. Exploitation is like, it's not always a negative thing. Sometimes we exploit things for positive things as well. So knowledge exploitation is one thing that I say, that we often say in our community, that if you are trying to learn something, if you are trying to make something good out of something, make something good out of something, you have to use it to the extreme possible level, so that you do really something that's really wonderful. Okay. So I hope you enjoy the session, and more importantly, learn something. Learn a lot from this session. So without further ado, I'd like to welcome today's speakers. So we're having two speakers, and I hope you guys know what the topic is about, right? So you guys might have seen the poster, which is like an introduction to rocketry. So today we'll be giving you a general introduction, which might be something that all of you might know. and then an insight into the mechanics aspect. So we'll be having two parts, which will be the mechanics part and the aerodynamics part. So for this, Vaishnav over here. Vaishnav is a second year BSc B.Ed student at the National Institute of Technology, Calicut. And then we have Abhiram, who is also a second year B.Tech mechanical engineering student from KUSAT, Kushi. So these two people will be like giving you guys an insight into the field, and you can interact with them. So this is an interactive session. You can ask your questions, and preferably you can post your questions that's in the chat box so that we can ask towards the end of the session. And if you guys feel like you have something critical to ask, you can actually raise your hands in between. So if the speaker allows it, we can have it in between as well. So it's entirely up to the speakers. So yeah, without further ado, let me invite Vaishnav to start the session. Vaishnav?
Yeah, thank you. So, hello there. Good evening to all. So, let's begin with our first topic. Is my voice audible to everyone? Can give me a thumbs up. All right. I hope the screen is being shared right now. So, let us begin with the topic, which is so we're going to take a very general topic here. We're going to just cover some general aspects of rocketry and mechanics here. So most of these things you might know, but let's just run over it. This is like a sharpening your what you already know. It's like a beginner's guide to rockets. So let's just begin. So first of all, can anyone tell me what is the word rocketry means? The word rocketry. Anyone? You can open your mics. Hello. I hope I'm audible. All right, so rocketry is nothing but it's just the science behind designing a rocket and launching rockets, right? How a rocket must design. So there are rockets for multiple purposes, and for each purposes, the rockets they differ in their designs and the components it has. So we will look at the fundamental aspects of a rocket. So first of all, let me start with a question here. So we can see the image of a GSLV here. I hope you recognize the GSLV, which is a type of a rocket developed by ISRO, and situated on a launch pad. So the question is, how does a rocket push itself from ground? How does it push itself from the launch pad and shoots itself into the atmosphere and then into the outer space? What makes a rocket go up? What pushes the rocket from the ground? Anyone?
Thrusters.
Yeah, thrusters. But what actually happens there? For what gives the thrust?
The thrust from the engines makes a reaction
Uh,
that pushes the rocket up.
exactly, the thrust from the rocket. But what actually gives that thrust to the rocket?
I think the burning of fuel.
Yeah, exactly. The fuel inside a rocket. The fuel must burn. So the rocket contains a fuel tank, and the fuel burns, and it burns at a very high temperature. So the gases inside uh, the the fuel tank, they have very high pressure. So at a very high pressure, they tend to escape their place. So at very high speed, these gases to downwards, and that's what gives the rocket a thrust. All right. So a reaction takes place, and the rocket gets a thrust, and we see that's when we see the rocket moving upwards. All right. So this is what happens. This is what causes a rocket to go upwards. And so we discussed what that the rockets have a fuel, and it has thrusters and all. So this is the basic components, the basic parts, fundamental parts of a rocket. It has a nose cone, it has a payload system, it has a guidance system, it has a fuel tank, everything. We will briefly discuss what all things are briefly each and everything, and its importance. The first thing is the nose cone. So we have observed, I think we always observe that the nose cone of a rocket, it always has a, sharp or rounded design, right? So can anyone tell me why do we have a sharp or a rounded design for a rocket, for the nose cone of a rocket?
To decrease drag.
Yeah, to decrease drag. So exactly. So we see it has a sharp edge. It can actually reduce the air drag due to air. It reduces the air resistance and all. If you have like flat surface and all, the rocket will experience a high level of air resistance and drag. So that's not convenient for a rocket if we want to send it out to space at a very high speed. And then we have the payload system. And the payload system is actually the most important part of a rocket. Actually, this payload system is what defines the purpose of the rocket. Whatever that is, let's say you want to launch a satellite into space. You put that satellite into the payload system. You want to put a Mars. You want to put a rover in Mars. You want to put a land rover in Moon, or you want some scientific instruments, all these things, even human missions, man missions to space, the humans reside in these payload systems. So payload system the purpose of a rocket. So we can say that payload system is one of the most important aspects of a rocket, as it defines the purpose of a. And we have the guidance system. Guidance, as the name suggests, guidance system is nothing but something which tells the rocket what to do. It has the navigation devices, it has the cameras, it has sensors, it has many other computers, communication devices. It all goes into here. And then obviously the fuel tank is there, and the oxidizer is there, the pumps and the nozzle. So now let me frame another question for you. Why do we need an oxidizer?
Because there is no oxygen in the space.
Exactly. There's no, but yeah, there's no oxygen in space. Because when the fuel heats up, you need to have a reaction. You need to have a combustion there, and for combustion, you need then only the combustion takes place. So you need an oxygen. So that's the whole. This is a very very fundamental design of a rocket. But you can. I'm not saying this. The design of each and every single rocket follows the same. The newer rockets are more complicated and complex structures and all. But let's just say that this is the most basic structure for a rocket. And next up, we'll discuss. So we discussed the fuel, right? Now we will discuss the different types of rockets, and we can differ rockets. We can differ rockets as per the kind of fuel they use. Okay, so first up, we will discuss about the solid fuel rockets. So these rockets, their fuel is a solid propellant, right? So as its name says, they will have something solid in it. And the important thing about them is that The fuel is so one of the most common example of a solid fuel rockets are just your fireworks, right? The fireworks that we use. They're also a type of rocket, and they have a solid propellant. And also some our PSLV, some parts of PSLV use solid propellant. And some features of solid rockets is that they have a very high thrust, right? So they have a very high thrust. So by saying very high thrust, I mean that at an instant when it takes off from the land, from the launch pad, it uses most of its fuel at that moment itself, right? So uh, it's produces very huge thrust instantly, and you use your fuel instantly, a huge amount of fuel. So that's a disadvantage of solid fuel rockets because you end up using most of your fuel at an instant itself. So, but to solve that problem, we have another type of rockets, which is the liquid fuel rockets. So the advantage of liquid fuel rockets is that they have a obviously they have a liquid fuel, but other than that, they come with their own unique features, which is that you can on and off the fuel system, the engine system, right? You can actually control the thrust level. You can just control how much amount of fuel you want to give. You can decrease and increase the speed. So this increase and decrease of the thrust is actually known as a throttling, the throttle of the rockets. So so liquid fuel, it comes with its own very specific features, which has its own advantages over the what we previously discussed, solid fuel rockets. So it's like our LPs. You can turn it on, you can turn it off, and also you can shut it down and you can restart it again. So uh, one more advantage is that it is not necessary that you should have a very high thrust at the point of you know when you take it off from the launching pad itself. You don't need to have very high thrust at that point itself. You can actually conserve your fuel for later uses when you are out in the orbit. It is not necessary for a rocket to continuously burn its fuel, right? You can control it. You can maybe you want to use the fuel to change your direction. For that and all, you might need to reduce the thrust. You might need to increase the thrust. For that and all, liquid fuel rockets are the best things, and they are used for mostly for large missions. For our Chandrayaan and all, they use liquid fuel rockets and all. Okay, so next up we have the another set of rockets, which is or the hybrid rockets. Hybrid. So from the name itself, we can just get the idea that they use a mixture of both solid and liquid. So it's that so commonly they use a solid fuel and they use liquid oxidizer. So the advantage of hybrid rocket is uh, that it's a middle ground between solid and liquid. So solids, they're safer than those two, and also very cheaper than the solid and liquid fuel rockets. Also, but it's not used for very high important missions and all. These are mostly used for experimental missions. It's just like liquid, but also it has characteristics of the solid fuel propellants. You can turn it on, you can turn it off, just like liquid propellant rockets. But it is also less complex. All right. So we discussed the main three different types of rockets, and other than that, there are also other special types of rockets. One of which is recently got popular, which is the reusable rockets. I think most of you are familiar with this picture here. I think this gained a huge uh, uh, popularity in the recent years. due to the SpaceX Elon Musk company, SpaceX, they invented reusable rockets. You can actually send a rocket out of space and bring them back. So earlier it was not possible, but due to the high advancement and new technologies, reusable rockets are a thing now. And then there are nuclear thermal rockets, and as the name suggests, they use the energy from nuclear reactions, but it's just a concept. It's not practical in the technologies that we have now. It's just a simple concept only. It's still in development. So, are we clear till now? I hope. Do you
Yeah.
have any doubts?
Yes.
All right.
Can you please tell me what kind of fuel is used in the solid fuel rockets?
It depends. Right. It might be some anyway, it's a chemical reaction that takes place there. So, in solid propellant, we can see it's some sort of chemicals. It's always it's what matters is the the state at which it is. It might be the solid and liquid. It might be the same thing, but just the state is different. Here it will be the liquid, and here it will be the solid one. So you can say that. So I'll get back to your answer later towards the end. All right, is that okay?
Is that okay?
Okay. So that's about rockets, and let's move on to our next topic, which is the introduction to Newtonian mechanics. I hope you are familiar to our great scientist Isaac Newton, and this was his famous. We also learned about his famous three postulates about motions. But before that, let's brush up with some of the basic concepts. So the first step we have speed, and speed is nothing but how fast an object moves. So is how the rate at which an object covers a distance with respect to time. So speed is nothing but how an object moves from a distance to from its initial distance to final distance. It's only the numerical value, right? Can be this from this position to this position, from this to this position. So it's a numerical value, but we are not talking about direction and all. So it can be, for example, you take your car and you go from one place, maybe from Trivandrum to Ernakulam. You take the whole distance, how much you covered, and that's divided by the that total time you took. That's your speed. That's the whole average speed of your travel journey. So that's you only take the whole numerical value of your journey, but you don't discuss about the direction at all. But when you talk about direction, you are talking about velocity. So velocity is nothing but speed plus direction. So you should see the difference here. Velocity is nothing but speed plus direction. When you talk about velocity, you also talk about the direction here. For example, an object which moves 60 with a speed of 60 kilometers per hour towards the north direction. And when you mention its direction, you're talking about its velocity of the object. So it's like that. Speed is distance divided by time, and it only tells about speed, nothing about the direction. Its unit is meter per second. And then we have velocity, which is displacement by time. We should note that it's not distance, it's displacement. So, and the unit is still the same, meter per second only. And velocity is what the addition is that it talks about direction at which it goes forward. Okay. So next up we have acceleration. So acceleration is one step forward of velocity, which is we are calculating the rate of change of velocity with respect to time. And here again, we are talking about the direction. We will talk about the direction, and also it's a vector quantity. So an example of acceleration is how much the rocket is speeding up from its that moment it took off to the orbit, we can say that rocket is speeding up from 0 to 100 meters per second. That's acceleration, the rate of change of velocity with respect to time. And the unit is meter per second square. And the next up, we have the mass of an object. So mass is all about how much matter constitutes in an object. And one of the common mistakes that we all make is that we consider mass equal to weight, but that's not true. Ever since we were born, we were taught that weight is something that our mass is, how much we weigh. But actually, weight differs, right? It depends on gravity. Your mass is actually how much matter you have. It's how much kilograms you have, and weight is how strongly the gravity pulls on your mass, right? So weight is like a force. It is like how much force the gravity exerts on you, and mass is purely how much matter is constitute in an object. All right. In the next step, we have force. So force is something that I think we all experience when you push a door or you pull a uh, very heavy thing. So that's a common experience, and it's Newton. We will learn more about force in upcoming slides. So these are the basic terms we should keep in mind. And now moving forward, we will discuss about the Newton's laws of motion, and let's talk about the first law of motion, which is the law of inertia. So first law of motion is also known as the law of inertia. So can anyone tell me what do we mean by inertia?
Sir, it is the state of motion.
Inertia is a state of motion. Can you be more clear about it? Okay, I will give you an example. Inertia
It is,
is, okay, somebody was speaking.
it is a state of motion that happens when a body is either it is an effect that either happens when a body is on in a state of motion or rest, when an
Yeah,
unbalanced force acts on the body.
exactly. So we can say that it's a body is at rest, or it's going in a uniform motion. So as per inertia, it will keep on doing it. If we try to act upon it, it will show a resistance to change its state of motion. Right? That's what inertia is. So I'll give you we can look at a real life example the most common or most relatable example is when we are traveling in a bus, right? For example, you're standing in a bus and the bus is going in a very high speed, and suddenly we experience suddenly the bus goes on a break, and the bus comes to standstill. But the person who is standing on the bus will experience a forward motion, right? Even though the bus has come to a standstill, in that instant, we will something pushes ourselves forward, right? So that's inertia. It's almost as if we are continuing to go in the same direction as the bus, even though the bus has come to a stop. So that's the intuition behind the Newton's first law, which is an object remains at rest or in uniform motion in a straight line unless acted upon by an external force. So the bus was going on, and we were going along with it, but the external force was that the driver applied a brake, and since the driver applied a brake, our state of motion changed instantly. But as a reaction to that, we were slightly nudged by it forward. So that's what the Newton's first law explained. So next up, we have Newton's second law. And Newton's second law is nothing but to just narrow it down to explain simply, we can just say that Newton's second law says that F equals ma. Is, or to make it more broader, we can say that the force acting on an object, which is F, to the mass of an object is multiplied by acceleration expressed as F equal to ma. So we can say that force by an object depends upon its mass and also the acceleration at which it comes. So we can also say that heavier object requires much force to accelerate, right? This we can say it's a dumbbell, and if we need to move it, even when it is at a rest and we try to pick it up, we're trying to accelerate it, and we require much harder force compared to when we are trying to throw a ball, which has a very light mass. So to accelerate this, we might require only very less amount of force. But when we are trying to accelerate something as heavy as a dumbbell, we require more force. So that's what Newton's second law is. Okay, so now let's move on to the third law, which is I think popular among everyone, which is very easy to remember one. For every action, there is an equal and opposite reaction. So, as the name suggests, we can example what we can give is, for example, we are in a boat, right? You're standing on a boat, and it's in a river, and we try to jump from the boat. So, what's happening is we are trying to push the boat away from us. We are pushing the boat, and the boat pushes us away. So we jump away from the boat. At the same time, the boat also experiences a force, right? So that's right. Our action was that we are pushing away the boat, and at the same time, the boat also exerts a force back towards us, because of which a reaction takes place. Okay, so we can connect this. Okay, that's a mistake here. It should be the title has a mistake here. It's like the third law. So can we connect the Newton's third law to the rocket propulsion that we already discussed? Anyone? Hello. Right, we can just like I said, right, we already discussed what makes a rocket push away from the ground. We discussed that the fuel uh, gets burnt at a very high temperature, and the gases from it go downwards. So that's an action, and to the reaction of it, it gives a thrust and makes the rocket move upwards. So that's an example of Newton's third law, right? So the action is that there's a very at a very high speed, gas goes downwards, which causes the rocket to have a thrust and makes it go upwards. Right? Is that clear? Hello. Cannot see the chat if you are giving thumbs up or not. Am I audible?
Yes, yes.
Okay.
Yes.
So I suppose that it's clear what I said just now.
Yes, yes, it is.
Okay. Okay. So next up, we have conservation of moment. So before getting into this, I will just tell you, I'll give you a scenario. So we already discussed that at F equals ma, right? As per Newton's second law, F equals. Now let's take a scenario where you have a car which is coming at you at a very high speed. At a high speed, let's say that the car has a mass, a set mass. It has a fixed mass. Let's say something around 100 kilograms or 150 anything. It has a fixed mass, but it is traveling at a constant velocity. Okay, it has a constant speed. It has a constant speed, and let's just say that the speed is high, but it is constant. It's not changing. So when it's not changing, we can say that what will be the acceleration?
0.
Yeah, the acceleration will be zero. So that means, and let's just say that some person came in front of this car and makes contact with this person. So what do you expect will happen? So in real life scenario, we know that it will bash us. We'll be crashed by the car. It will be a very bad accident. But we just saw that the speed is constant, and since the speed is constant, the acceleration will be zero. So that means if you put this into this equation, the force exerted by the car should also be zero, right? So that creates a problem here because if the force is zero, then that means the car shouldn't affect this person. If it is coming at a very high speed, it should not affect us. So what's the another thing which is happening here? So what are the things that we are missing? Can anyone provide a hint or explain it?
The
All right.
car has momentum from the velocity.
Yes, exactly. The car has a momentum, but other than that, before we go into momentum, let me explain one other thing that when the car is speeding up, and when we come into contact with the car at a very small momentary time, at a very small instant, the car actually decreases its speed at a very small instant, and because when it comes into contact, now at that moment the acceleration decreases sharply. And what happens when the acceleration decreases? So let's just say that the speed decreases for a very small instant. The speed decreases. When the speed decreases, the acceleration also decreases. And when the acceleration decreases, it's called negative acceleration. And when the acceleration decreases, this changes, right? This value changes, and so the force rapidly increases because the mass of the car compared to the person is very high. So that means here the force will be very high, right? And this force is so high that it will cause a very bad accident. So that's one thing. And other than that, just like you guys earlier said, the momentum. So what is momentum here? So momentum is nothing but it is mass times velocity. So the momentum of the car here would be its mass and also the velocity it comes, right? So we usually define momentum as P equals m into v. So the mass of the car times velocity. It is coming at a very high velocity and it also has a very high mass. And but the thing about momentum is that it likes to conserve itself. So we in physics we consider the car as a system. It's a system. So right now the car it is a independent system, and now a person comes in front of it. It's another system. But when it comes into contact, what happens is that this becomes a single system. It becomes one system. So the car's momentum, let's say P1, will be transferred. The same amount will be transferred to this person here. It will become P2. Right? This will become equal. So what was this? So earlier, this person's momentum was small, but when they became in contact, this P2 became a very high value. So this person will experience very high momentum, because of which he will be thrashed away, and that's what we see in real life. All right. So I guess you guys are clear with that. So now we are ready to move on to the next speaker. He will take the next topic. And towards the end of the session, if you have any doubts, I will clear them. Just put it in the chat box. Okay. So I would like to welcome Abhiram next up. Thank you.
Am I audible? Just wait a moment. Let me present. I think the presentation is visible, right? Can anyone just turn on your mic and say, because
Yes, it's visible.
Yes, sir.
okay, fine. So good evening, guys. Hope I am clearly visible and audible. Also, my presentation is visible. Then let's start. I am Abhiram, a second year BTech mechanical engineering student from School of Engineering, Bijith. So I am also a member of Fuel Space Club. Hope you guys are mainly from classes 11 and 12. So the role of me in this project is to give you some introduction about aerodynamics. So you might know that aerodynamics itself is a very large domain. So it comprises of many other disciplines, including mechanical engineering. So in such a short period, I won't be able to provide you with A to Z of aerodynamics. So what I planned is to just give you some really basic concepts of aerodynamics. So actually, this topic is completely mathematics. So it's a Herculean task to explain things in a simple manner without using such heavy maths. However, I will try my best. So I am also a student trying to learn these things. So don't expect mastery from me. And when we talk about aerodynamics, the first thing that comes to our mind will be definitely fighter jets, normal passenger planes, rockets, but it's really far from that basic stuff. So we can start our session with a little history, I think. In 1588, in between the famous Anglo-Spanish War, Spain made a very powerful naval fleet consisting of very huge warships equipped with very high and advanced weaponry. But on the other hand, the navy of Queen Elizabeth I faced them with little sleek warships with relatively uh, lighter weapon systems and less capacity. So the outcome of war was too predictable, right? But the war of sea giants and those little ships never thought to bring a really suspenseful end. However, finally, when the smoke settled over the waves, Queen's Navy came out as champions. Till then, the concept of ships and or any body moving through a fluid was just dependent on buoyancy and its capacity to carry as much goods. So, but England won this war by making breathtaking maneuvering and easy aiming with their lighter weapon systems. So from there onwards, the concept of design came into play. That was the origin upon which we made all these flying and floating stuff. So we can understand the variation of design of rocket nose cones and the base shape of a re-entry module from space. There comes the aerodynamics. If you ask me what is aerodynamics in standard textbooks, aerodynamics is just the study of flow of air around a body moving through air. It's simply a subsection or a class of fluid mechanics where we learn the interaction between fluids and body. Okay, so in aerodynamics, we learn why a pigeon can fly and why not a hen, and why do we design parachutes in some particular way. Why do we make the front tip of our fighter jet pointy? And why did Mitchell Stark and Dale Steyn create such killer swings? So let's simply analyze a body just remaining in rest at a flowing liquid. Okay, so here the flowing liquid will exert a force on this direction, slightly inclined to its horizontal and vertical axis. That is the actual force exerted by the moving fluid on the surface of the body. I think most of you might be familiar with the resolution of vectors. So we can resolve this inclined component of force exerted by the moving fluid into two, a vertical component and a horizontal component. The vertical component of this force is called lift, which tries to move the body upwards. And the horizontal component is called drag, which resists the motion of the body through the fluid layers. And there is a specific ratio called lift to drag ratio, in which we will find the ratio between the force causing lift and drag. And this ratio is quite important in when it comes to the designing of wing of aircraft and all. We will discuss about that later. So if we consider the motion of the body also, the force exerted by the body in the fluid also, the frame changes, and we can see two more forces, mainly thrust and weight. So as you know, lift will push the body upwards, drag will pull the body backwards relative to the motion, and the concept of drag is almost similar to friction and not exactly the same. And the thrust will move the body to the desired direction of motion, the direction in which we apply a force. And don't make the misconception that the drag and weight are unnecessary for a perfect flight of a body. Just like friction itself, drag is also a necessary evil. So our focus is mainly on lift. As you know, for many decades, scientists and engineers thought it was a magical force like the one moving the carpet of genie. And let's discuss how this magical force is made. If you look at this diagram, you can understand the things from the diagram itself. When an airfoil means the cross-sectional view of the usual shape of the airplane wings. If you observe that section, it's a special shape, right? It will allow the air to flow through the upper surface as well as lower surface. Due to its this special shape, it's not symmetric, right? So this special shape will allow the air to pass through both the surfaces, and the air passing above the wing will be moving very fast, and the air passing below the surface will be moving relatively slower. That means very slow compared to the upper surface. So that's where the Bernoulli's principle rises. You might know about Bernoulli's principle. What is Bernoulli's principle? It's simply the conservation of energy, right? So in Bernoulli's principle, the sum of pressure energy, kinetic energy, and the potential energy of a flowing fluid under some specific constraint, it will be constant. Don't worry about that part. I can make it a bit clear. So According to this, where velocity is high, that means the upper portion, there the pressure will be less. So below the wing, where the velocity is low, the pressure will be high. So as you know, based on the concepts of equilibrium, the particles will always travel from high pressure area to low pressure area. So that's how the air will get pushed from high pressure lower surface to the low pressure upper surface. So this push of air particles will increase. That means that is a lift creating the motion. So this lift will increase till an angle of attack, and that angle is called the critical angle of attack. And I'm not going that deep into such technical terms. You can ask the doubt if you want. So that's what the lift is called and how the lift is made. And also, according to Newton, based on basic mechanics, when lift becomes higher, when the lift becomes more than the weight of the body, it will start to move up, right? So that also, not only that, but also according to Newton's laws of motion, effectively when a wing is moving forward, it is pushing the air backward. Hence, according to Newton, the air will give a push to the plane to the front direction. So that is the simple dynamics behind the lift, and I know here we have some limitations for making you understand this concept through an online platform. However, you are free to ask doubts after the session. So as that is the case, you will definitely wonder why a fast moving bullet or an arrow is not able to generate lift like a plane moving. The answer is pretty easy. If you observe the geometry of an arrow, we can find that it's symmetric. It is symmetric along its axis of motion, right? So there won't be a pressure variation, or there won't be a geometric asymmetry that will lead to zero net force. I repeat, net force is zero. There are forces, but they will get cancelled each other. So it won't cause any motion or push or pulling upward or downward direction. So that's why it's quite important to learn about the shapes that I previously called airfoils, which are able to generate lift and maintain stability with least drag force. Okay, so if you check the chart I have given here, you can see 6 different shapes. It's just a thing with historic touch, so just some theoretical stuff. And the first one was designed in early times when we need to generate high lift, not high velocity, only high lift. We needed to fly high. But the fact is that as lift increases, it will also bring high drag. As I've told earlier, the lift and drag are made from same parent force. So when the lift increases, it will also bring high drag. Hence the speed of aircraft was pretty slow with that early airfoil design. The next one is it was made to the second shape, that means a later airfoil, that was made to find a common ground between lift and drag, and thereby providing a near perfect lift to drag ratio. And this will work best for medium speed passenger planes where we don't have the need of very much lift and very high speed. And the next model is Clark Y airfoil. It's used in subsonic speeds, as also in the previous case. It is not quite famous one when it comes to cargo transport or defense applications, defense industries. But it is really trustworthy, and we are using this in some training planes like Cessna in our aircraft pilot training industry. So it will feel like how a Maruti 800 feels for a fresher riding cars, and it can provide better stability. And the next model is laminar flow airfoil. and this is able to provide a very smooth airflow without significant amount of drag or turbulence or stall. I will explain later. And this was used mainly in an old lion of the fighter jet industry, P-51 Mustang. And the next one is circular arc foil. It's just symmetric and very thin. And the ability of this body to produce lift under less velocities are not appreciable, but still it holds good at high speed flights. It We can use it for making the flight at very high speed stable, and it can be used at supersonic speed. Supersonic speed means the speed just in the boundary of the speed of the sound. And the next one is the real dawn. It's double wedge airfoil. It is perfect when it comes to handling shock waves and such sound barriers. This is usually used in missiles, rockets, and some very advanced fighter jets. The fact is that they can stay stable even at a speed above Mach 2. But in the modern advanced world, we cannot simply take advantage of the wing shape only to create more maneuverability and speed. So we need to add some more systems to increase the speed and provide better maneuvering. So if you don't know, maneuvering simply means the ability of an aircraft to change its direction course within a very short time. Okay, you might have noticed that uh, a passenger plane like Boeing 777 cannot take a sharp turn like an F-16 or F-22 fighter jets. So that's the difference between maneuverability of these two class of aircraft. So I hope maneuvering is clear for you. So if we check a normal passenger plane like this one given the picture, we can find a part named aileron, which is located at the wingtips, that red color portion. And this mainly controls roll. Roll means the tilt towards left or right. And next is rudder. Rudder is that blue color region at the tail end, and it is found on the vertical tail, or it's also called fin. This controls the yaw, and it helps in turning the nose left or right. This part we mainly use in situations like a hard landing in crosswinds or such situations. And next are elevators. These, as the name indicates, it will help us to rise or lower the nose cone and increasing the altitude. This can be used in takeoff, ascending, descending, or landing. And the next one is a spoiler. The name is itself a spoiler. Okay, so they are placed on the top of the wings to slow down the aircraft. And this will be fully deployed when we are landing, and this will keep the plane on runway. That means it will prevent the bouncing of the aircraft after the impact. And then the slats, they are found on the leading edge of the wings. This will help us to keep the flight away from stall. If you don't know what stall is an unwanted effect caused by the separation of air streamlines from the wing surface. I think in this situation, I'm not able to explain the stall in such short time and in such a setup. So, however, slat always works together with flaps, and I think we have discussed enough about aerodynamics related to planes. Now we are going to focus on the aerodynamics of rockets. If we consider the forces on a rocket, we can find all the force found on the plane, right? But it is in a different manner. So the main force, thrust, you can see the thrust will push the rocket upward. This is created by the exhaust of the rocket from burning fuel, as Vaishnav has already mentioned in the session. So, and the weight of the rocket will act on the rocket through its center of gravity downwards. Also, the drag, it will push the rocket against its upward motion. And on the other than the plane, lift is very less, and it is not that much important, since it will only help us to keep the rocket stable. I mean, lift is not that much significant when it comes to rockets. For an aircraft, lift is hero, and for a rocket, thrust is hero. And when it comes to the shape of the nose cone, mainly the shape of the nose cone, you have you ever seen a perfectly spherical or perfectly planar surface at the top of any rocket? No. Why? It's not because the Supreme Commander told them to make the rocket pointy or to make it look scary. It's because the sharp nose cones will reduce drag, and the smooth cylindrical body makes the air flow easily through the surface. Also, those thin fins at different points you can see on the body of rocket, it helps to maintain the stability. We will explain that soon. And when we talk about the stability of rockets, we cannot avoid the concept of center of pressure and center of gravity. It's not that easy to understand without some prior knowledge of mechanics. However, I'll try my best to explain this center of pressure and center of gravity concept lightly. So, the center of pressure of a body is a point where the total pressure will be experiencing when it is immersed in a fluid. It is just similar to center of mass. Okay, and the center of gravity, as all of you know, is a spot where the whole weight of the body is considered to be acting. So when the center of pressure stays below the center of gravity, that you can see in the first figure, the rocket will be stable. So the fins we used in the rocket, it will push the center of pressure backwards from the center of gravity in a theoretical manner. Okay, but when the center of pressure is above the center of gravity, it will get into an unstable equilibrium in which the slight variations from its neutral position will cause a chaotic variation from the flight path. So these 2 points can be only understood through the proper understanding of moments and some moments, that means some advanced part of force. So as you guys are not that much aware about the mechanics of a body, we are dropping that concept for now. So now I think I'm adding an additional point. It's actually nothing but a sound barrier and shock waves. You might have heard and seen these Mach cones and will always wondered why this happens. The basic concept is the air carries sound as pressure waves. Okay, the air will be like the stack of sound as pressure waves. So when a body moves faster than sound through air, the air connected with the body cannot also move with that same speed. Not the complete particles in the three-dimensional space, only the air particles which are tightly connected to the surface of the aircraft cannot move with the speed of that body, and this will cause a pileup of air particles around the aircraft. And when you use an aircraft which is enough to pierce through this region, we will hear a huge voice which is called sonic boom. It will be very huge voice. So for decades, pilots and engineers thought they could never overspeed at the speed of sound, which means breaking the sound barrier. But now, as you know, the technology is much advanced, and we are always solving the all challenging things, the all so-called challenging things, and So you can see that dense region around the aircraft, that dense white regions looks like some smoke, and this portion is also called Mach cone, as I already mentioned. Mach is actually a unit we use to measure the speed of a body with respect to sound, the speed of sound. For that, the speed of sound is taken as a reference of Mach 1, and if the speed is less than Mach 1, it is called subsonic, the speed in which the normal passenger planes will move. And if the speed is in between zero point 0.8 to 1.1 or 1.2 Mach, it can be called transonic. That means you are approaching, or you have already approached the speed of sound. And if the speed is above 1 Mach, it is called supersonic. And you can see so many fighter jets operating in the supersonic speed region, which is much higher than the speed of sound. And even above that, there is a region, we have called it as hypersonic region, which mainly consists of the speed range above Mach 5, and this can be found in missiles and related stuffs. I think you might have heard about the intercontinental ballistic missiles and all. You might have heard about the BrahMos and things. I'm not entering into that part now. So above Mach 5, it is called hypersonic region, and so many missiles and all operates in that region. So in the case of rockets, they reach supersonic speeds within very short time, within seconds, and it will be faced by these problems like sound barrier and shock waves. So for mitigating this effect, we are using proper design and aerodynamics. So and you can, if you observe a rocket, you can find so many things which you might feel these things are unwanted, why they are making things this much complicated, and those old regions which feels unwanted, or which feels weird on the surface of rocket, that portions, that regions, or that parts are the subsystems which we are used to make our flight path stable. They have a very significant role in mitigating the effects of shock waves. And I think that's all I have to tell you. The biggest problem I had while preparing the material was that, as I said, aerodynamics is a very vast subject. So the selection of topics which has to be presented in front of you took a lot of time actually. I had a lot of things to share with you, and uh, we had constraint of time. So I am ready to hear your questions, and I am ready to sharing you what I've learned. And so I'm ready to hear your questions, and I will answer if I know. As I said earlier, I'm not an expert, so just feel free to ask. We all are learning. So thank you for listening.
Think we can move on to the Q&A.
Yeah, we can.
Yeah, can you guys see me and hear me right now?
Yes.
Okay. So I hope you understood whatever that is presented here today. So as I said in the beginning, this was an introductory session, and this is aimed at giving you an insight into the field of rocketry, or what are the prerequisites that you might need to know before you enter into the field. So yeah, thank you Abhiram and thank you Vaishnav for that wonderful session you gave today. It was informative, and I'm pretty sure that these guys might be having a lot of questions to ask you. So I'm not taking much time here. So, like I said, this is the first session out of the 5 sessions that we are planning, and the next session will be on Sunday. So, what we are thinking of right now is 2 sessions. So, the first session will be in the morning, and the next one in the afternoon, maybe evening time. The timing is already shared in the group, so we'll share it once again. So if any of your friends are interested, are yet to register, ask them to register soon because we'll be providing the link for the live session for only the registered participant to attend in the Google Meet. The YouTube stream is available to all, and this session will be available online in our YouTube channel, and the link will be shared in the group. So ask your friends if they are interested to join this. It is absolutely free, and yeah, the main our intention, as I said in the beginning, is to spread the awareness and make you guys give you guys an exposure to the field of rocketry itself. So I hope you enjoyed the session, and the details regarding the next 2 sessions will be shared in the group shortly. And yeah, I think we can move on to the Q&A session right now. Thank you, Abhiram and Vaishnav, for this wonderful session. We can. So, Drishya, are you there right now?
Yes.
So, can you? I mean, you can get on with the Q&A session then.
Okay. I can see some few of the questions in
Yeah,
chat
fine.
box.
I think Abhiram, Vaishnav, you guys can decide how you want to take it. If you want, you can read from the chat box, or if you want to ask the person, it's absolutely fine. So you can. I'm leaving it up to you. So, and yeah, Drishya will be moderating this.
I think it will be better to ask with those persons so they can explain their things clearly.
Yeah, fine.
Okay, Haran.
Okay, so the doubt I have is, so we do use cryofuels in rockets, right? So are cryofuels a part of liquid fuels?